So,
Notebooks out?
what's up?
Notebooks out.
Yeah. Nora, if you will need to set up your shared notebook, you and I can handle that at the end of class if you're not sure what to do, or if one of your friends next to you knows what to do still, they can tell you kind of how to do it. It's quick, but you're welcome. If not, you and I can get it at the end. Okay?
Did he start golfing on your side?
All right. So on the first day, we'd ask you guys to, as your first homework quiz, to write down as many things as you knew about triangles. I'm just going to table that for a little bit. We'll come back and pull those out and talk about them here in a little bit. But chapter 1 is largely a review of things that we had done in previous algebra courses. So trigonometry is a little bit of a union of algebra ideas and geometry ideas, and they kind of like fit together to make one coherent subject. So we're going to start with some algebra review ideas. When we get ready to start trigonometry, we'll go back and review some of these salient parts from geometry. And then we'll start kind of like building off our new. Okay? Okay. So we're going to start with just talking about functions. And all the notes that I'm doing are based on, if you look in your OneNote, Chapter 1 lessons, these are like the book pages that all the notes are based off of. Okay? Just as a reminder. Oh, that's not what I wanted to put on. This one. Good Lord, bless you. All right. So, functions. Does anybody remember what a function is? Allergies?
Stay away from me. What? I don't know.
Anyone with what a function is? Do we remember? It has. Okay, so this, a function. Yeah. Okay, so this would have been the fundamental idea from like your Algebra 2 course. Really, Algebra 2 is going to be a survey of different types of functions. So in mathematics, at the most fundamental level, we have the mathematical object called a set. A set is just a collection of numbers or other mathematical objects with no repeating members to the set. So like 1, 2, 3 could be a set. But like we wouldn't say 1, 1, 2, 3 is a set because it has 2 ones in it. Everybody's okay with this idea?
Yeah.
So a function is a map or a description or a set of instructions that's going to pair the things in one set up with the things in the other set in a certain way. And that certain way is that if I have one thing in this set can be paired with exactly one thing in the other set. So I can't have one thing over here that goes to 2 places over there. Everybody's okay with that? Okay. So that's what we mean by a set. So, or a function. So say, bless you, cheapers, creepers. When you said you sneeze a lot, I guess you were...
No, yeah, it's a problem.
Yeah. Are you sure you don't have allergies?
No,
No, you're not sure?
not anymore.
Okay. Yeah. It's It's a lot of
I
sneezes.
went to the doctor and I don't have to take my audio medicine anymore, so I think I'm good.
Hmm.
Might pop that down.
So again, we say a function from a set D to a set R is an assignment, a rule, a mapping. It's a set of instructions such that every element, or just member of the set, so every number, maps uniquely to an element in R. So again, some member of that other set, another number. We say that the input values, we call those the domain. That's the members of set D. And the output values are the members of set R. We call those the range. Is this vocabulary sounding familiar? Okay. If it's not, or if something's not clear, stop and say something, and we can talk some more. So one way I can represent a function is with something like this, which is called a mapping diagram. So this is just a visual representation of that definition we just described verbally. So the set D is the circle that I've drawn there. And the three dots inside the circle are the members of that set D. I've labeled them as just like x1, x2, x3. The set R is the other circle that I've labeled as R. The dots inside of that are the members of that set R. I've labeled those members y1, y2, y3. The blue arrows going from the members of set 1, or of the set members of set D to the members of set Y is my description. That's my function. That's f in this case. So if I look at this arrow, what this is saying is that f of x1 is equal to y1. Because x1 pairs with y1, or if you prefer, we can write it as an ordered pair, x1 comma y1. Is everybody okay with that? Okay. Does the drawing that I've just made represent a function? Yes, because everything in the domain is going to exactly one place in the range, right? Nothing from the domain is going to two places, and everything in the domain gets used. Okay? So far, so good? Pace okay? Okay. If it's going too fast, you can tell me. Sometimes I just get excited about the math and get going. So if that happens, you can tell me to slow down, or you can tell me that to explain something again, or just that you don't understand. I might ask you, where was the last place you understood, so I know how far back I need to back up or something. But so we'll do another example here. So I'm just going to draw another mapping diagram. Does this represent a function? No. Great. Why not? Excellent. Let's actually use a different color there. Since the domain value x3 doesn't pair with anything, that does not meet the classification for a function. It's not a function. Everybody's okay? See, do this, that. Does this represent a function? Yes is the answer. Does it matter that little old y3 is unpaired? No. Why not? Because it's in the range, right? The domains are all covered. They're all going to exactly one place. Function. Everybody's okay with that idea? Okay. So you guys you learned more last year than you thought, right? This all seems okay so far. Is this a function?
No.
No. Very good. Why not?
X1 has 2.
Excellent. Yeah. The problem is x1 that has 2 possible outputs. Is everyone okay on that? Great. How else could we represent a function other than with a mapping diagram? Is this how we often do it in math class? No, right? We might use instead a set of ordered pairs. So to show that something is a set, we start by writing the squiggly bracket. And end with the squiggly bracket. And then I just have 3 ordered pairs in there. So this set of ordered pairs also could represent a function. Does this set represent a function?
Yeah.
Yes. Why? Well, all I'm really looking for is that there are no repeated elements in my domain. So as long as my x's are all unique, set of ordered pairs is going to be okay. What about this one? No. What's the problem? Yeah, the x's are repeated. How about this one? Is that a function? Yes. Does it matter that the y's all repeat? No. All we care about are the x's that are all different. You guys are doing a great job. Look at all this stuff you remembered and you didn't realize you remembered it. Right? And this is good. This is like the foundational pieces. All right? Is this how we usually represent a function? No, right? Well, another way we could use that or represent a function would be with a graph. So let's say this red line is the graph of y equals f of x. Does this represent a function? Yes. How did you know? Well, I can draw a straight line that's not a function.
It doesn't go back over x.
Okay, so there's no repeated x coordinates, right? What's the easy way to check to see if there's a repeated x coordinate? The vertical line test, right? So usually we talk about like trying to see, is there any place where I can draw a vertical line that intersects the graph more than once? We call that the vertical line test. If I can do that, draw a line that intersects the graph more than once, it's not a function. But here you see no matter where you draw your vertical line, it's just going to hit the graph one time. So that's a function. And your explanation could be just because it passes the vertical line test, right? And this guy you say is no, why not?
Does not pass the vertical line test.
Yeah, easy to see that there's a lot of places where I could draw a vertical line and it would fail the vertical line test, right? Because it intersects the graph more than once. Everybody remember doing that? What's the trickiest way that you could, what's the trickiest thing Mr. Kulik could do to try to fool you with a graph? Well, I could do something like, what does it mean when there's like a little open circle on a graph? That's like it's called a discontinuity, but basically that's indicating that there's a missing point there, right? The graph is missing a point in that spot. So we could do that and still put like an extra point down here, and this is a function still, right? Because even though it seems like the graph would, or a vertical line could intersect the function twice, really there's no point where the open circle is. Does that make sense to you guys? Is that okay? We'll talk more about discontinuities in another section or two. Okay. So a lot of times our functions are represented as graphs. That's pretty common, right? But what's the most common representation we have for a function? An equation, right? So what if we say the equation y equals x squared plus 2. Does that represent a function? Okay, how do you know that? Wild guess. That's okay. It's true, but it's often not clear just by looking at the equation whether that thing is going to be a function or not, right? What could we do with this? We could graph it. We could change its form, look at its graph, and apply the previous method. Everybody's okay with that? Now, this particular problem, it's not unrealistic for me to think that you could graph this in your head based on your Algebra 2 class. This is something that I'm sure you graphed in Algebra 2 and at one point would know what this was going to look like enough to where you could tell if it was a function or not. Does anybody recognize this kind of an equation? It's not a slope equation because it's not a line. Starts with a Q. This is a quadratic equation because it have the x squared, right? That should ring a bell. What does the graph of a quadratic function look like? Does anybody remember? The graph of a quadratic, what does it look like? Mm-hmm.
I can only think, because I think I know.
I know what a graph looks like.
It looks like a U, right? It's either going to open up or it could open down, right? Sure. Like a tulip or something.
Oh, yeah.
Okay. Now, does it matter if all I'm trying to do is determine if this is a function or not, whether the graph opened up or down? Not really. In this case, do you remember how to tell if it opens up or down? So you look at the leading coefficient, and if that leading coefficient is positive, it should open up. If it's negative, it should open down. And then if all we have is a constant term next to it, that just tells us that the graph would be translated up 2 units. So the function should look like this. In which case, this would would pass a vertical line test, and we would tell it's a function. Is everybody okay with that method? That's typically the easiest way to do that. Now let's pretend you didn't remember any of those things from last year because you didn't. How else could we get the graph out of this thing? Plug it into the calculator. Let's review how to do that. Okay. So you're going to want to start by turning your graphing calculator on. Sure. If you just want to watch, that's fine. If you want to follow along, that's okay too. Okay. We're going to turn our calculator on and begin by pressing the Y equals button. The Y equals button is located in the upper left-hand corner. The first thing that I'm going to want to do is if there's anything else in my Y equals menu, I'm going to get rid of that by just pressing the clear button. So I might move up or down to different slots if there's other things in there and just clear everything out of there so that I have a fresh, clean slate to work in. Is everybody okay so far? Okay. I'm then going to type in x squared plus 2 because the y equals part is already on my calculator, right? It says y1 equals already. So I don't have to type the y equals part. I just have to type in x squared plus 2. So the X button is here located next to the green alpha button. And then the squared button is down there under the math button, under the green one. Oops, that's not the one I want. I couldn't read it. There it is. And then I'll type plus 2. Everybody okay? Now to make this thing graph, what I'm going to do, because I don't know the last time I used my calculator, my window could be all junked up. I don't remember. It's been 3 months since I've turned this on. I'm going to press the zoom button and pick command 6 that says Z standard. That's going to reset my window to the typical -10 to 10 on X and -10 to 10 on Y. And that's usually going to be a good picture. So I pressed zoom and picked option 6, Z standard, and then pressed enter. And this is what I get, which is exactly the picture we sketched below with what we remembered from Algebra 2. But if you didn't remember all those details today, which is totally fine, not surprising, you could have typed it into our calculator and gotten a response. What if, however, it was written as this way? Can I type this into my calculator as it's currently written? No. What would I need to do in order to get it into a form that I can put in my calculator? I got to get the y by itself. Perfect. So to do that, what would I do first?
Subtract the 2.
Great. Subtract the 2. Bye, Delaney. Good luck. Get some spikes or something. Kills. Kill! Okay. And then what should we do next? We've subtracted 2 from both sides. Great. So square root both sides. Now, what do I have to remember when I square root both sides of the equation? That's true, but this particular operation of square rooting both sides creates something else that when I do it to both sides of the equation that I have to remember about. It's okay. So notice that if I take 2 squared, I get 4, right? If I do negative 2 squared, I also get 4. So if x squared is equal to 4, x could be 2 or negative 2, correct?
Yeah, it's imaginary number, right?
So I need plus or minus. Okay. Can you grab that door for me? That's lunchtime is happening or something, and it's distracting me. I'm sure it's bothersome for you. Thanks, Jake. Appreciate it. Now, we have the y by itself, right? Fantastic. Do we have a plus or minus button on our calculator? No. So what am I going to do? Mr. Kulik led me to believe that I could get this into my calculator.
X squared plus 4x squared minus 4.
Easier than this. I'm just going to type it on 2 lines. I'm going to do one equation, y equals square root of x minus 2. And my second is y equals negative square root of x minus 2. Make sure when you're typing the negative, you're using the negative sign and not the subtraction symbol. You'll get a syntax error on your calculator if you try to use the subtraction symbol instead of the negative sign. So I'm just going to type it in that way. I'm just going to use 2 lines. I'm going to have 1 line for the positive and 1 line for the negative. And then I'm just going to press graph. I'll wait here as it looks like people are following along, just for a moment. If I hit graph now, that's my picture. And I can see, is that a function?
Yeah. No.
No, why not? Fails the vertical line test. Excellent, yes. Is everybody feeling so far so good? The pace is appropriate for you guys. Okay. Yes, sir. Absolutely. So, I want to talk about when we write an equation, we have to be a little bit careful here. So, what we've done in these last 2 instances is we made an assumption when we did this. Now we did this automatically because it's kind of standard practice to make this assumption, but we made an assumption. This is a hard question. Does anybody know what the thing is in the background that we assumed was going on?
Where?
So in both these two examples where we looked at y equals x squared and y equals x squared plus 2 and x equals y squared plus 2, we made an assumption when we decided if these were functions or not. Nora? Sure. Now, let me explain what that assumption was. We assumed that the x was the independent variable, that represented the domain set, and the y was the independent variable representing the range set.
Yeah, I don't know we got that.
No, it's
I
subtle.
have no idea what that just happened.
Now, if I had flipped that assumption, if we had assumed that the y was the independent variable representing the domain, y equals x squared plus 2 would not be a function, but x equals y squared plus 2 would be a function, right? And vice versa. So there's a little bit of ambiguity here when we write the equations as y equals something, right? Because we don't really know for sure what's the independent dependent variable. So for example, if we had written, say, like s squared plus r squared is equal to 4, which one is the independent variable, which one is the dependent variable? It's not clear at all, right? Which one should be which, because I didn't even use x and y. So there's not even like a standard, Mr. Kulak, there's not one by itself that would kind of indicate to me, okay, maybe that's the dependent variable. There's not x's and y's for me to indicate that, like, hey, that's usually what we do is, what do I do? So there's a little bit of ambiguity built in if we're just using like two variables. What we can do to make that better is we can use function notation. So instead of writing this, say, as y equals x squared plus 2, instead we can write f of x equals x squared plus 2, because that guarantees to me that x is the independent variable, because the other variable is a function of x, right? So it means the same thing as a y equals. All it is doing is giving us the extra bit of clarity to tell us for sure whatever that variable is inside of our function is the independent variable. Is that okay? So it means the same thing as a y equals. You can treat them exactly the same. You could use them interchangeably. It's just adding an extra piece of clarity by specifically spelling out to you that whatever is that variable inside of the f, that's the independent variable. Okay with that idea? Now, another thing that function notation allows, yes, sir. Of course. Another thing that function notation allows us to do and saves us a little bit of time. What if we wanted to say plug x equals 2 into y equals x squared plus 2? Well, that would tell us to do something like this, right? So we just replace the x with a 2 in our equation and then simplify things down. Everybody's okay with that? But look at how many words it took to do that direction. If we use function notation, That's all we have to write. It's the exact same direction. It's telling us to just plug 2 in for x into our function, but we're writing it with symbols, and that's a lot less writing, which is, as a mathematician, we are the laziest people in the world. If I can make up a clever way of describing something that takes 4 symbols instead of 8, for sure we're going to do that, which is irritating as a student. Like, why can't you just say what you mean? Why do we need a symbol for it? But the reason is that it's less writing, and that's why we do it. So it's just kind of like an abbreviation. Does everybody remember doing this in your algebra classes in the past? Probably 1 and 2 you do this, right? Okay. That was section 1.1. Okay. Everybody feels pretty good about what we did here. Again, did we do much in the way of computation? No, it's mostly just kind of like definitions and like some notation. Not a lot of like what we would traditionally call math. Although I think that the definitions and notation is like 50% of what we really mean in math. That's often the hard part. We're going to look at section 1.2 next. Okay. So in section 1.2, we're going to be talking about how we can describe the domain and range for functions. So when doing this, we have like 2 different situations. We have things that are discrete versus continuous. So an example of something that's discrete would be a set of ordered pairs where there's finitely many ordered pairs. Right here, how many ordered pairs do I have? 3, right? There's not an infinite number of them. There's just 3. In that sort of situation, to describe the domain, because there's a finite number of things in my domain, I can just use the set notation and list them. What are the items or what are the elements in my domain? Just the x coordinates, 1, 2, and 3. And then what are the things in my range? The y coordinates, which are 1, 3, and 7. Does it matter the order in which I write those elements? No. Sets are unordered, so it doesn't matter the order you list those. Everybody feels okay on that? So let's look at a continuous example. So really anything that we'll write with an equation is going to be an example that's continuous. By continuous, we mean it's going to contain an infinite number of points. Because if we graph this thing, we're going to get a curve, right? In geometry, how many points make up any curve? Infinitely many. So we certainly cannot list them, because we would never be able to finish. There's infinitely many. I could list points list values all day till I get dead and gone, and I'm still not even going to be halfway there, right? You just can't get there. So we're going to use a different notation to describe domains and ranges in continuous situations. Okay, what we're going to use is something called interval notation. So for an interval notation, we're going to have a lower bound, so the smallest possible, or value that's less than or equal to everything in the set, and then an upper bound. Actually, let me rephrase. A lower bound that's something that's going to be strictly less than everything in the set. Upper bound, something that's strictly greater than everything in the set. And then we're going to add either a parenthesis or a bracket to the end to indicate whether that lower bound is included in our set or the upper bound included in our set. So the bracket is going to tell you that that number is included. The parenthesis would tell you that it's not included. It's basically saying, okay, everything between here and here, that's what we got. Because we can't list them all separately. There's too many of them. So we're just going to say everything between here and here. Do I count the ends? Do that, count that end, but don't count that one. That's it. That's the idea. Okay, so let's go back to our actual example and try to write the domain for this. So what do we know about square rooting numbers? Where does square rooting numbers get us into trouble? You guys were telling me this earlier. Negatives. What happens when you try to square root a negative number? Not a plus or minus. It was the i's. Yeah, you guys wanted to bring that in earlier. We were getting to it. So if it gives you an I, that was undefined for a while, right? Everybody agrees? Like if I did the square root of -1, prior to talking about i's, we just said that was undefined. So those are not going to be part of our domain. Anything that outputs an imaginary number, not part of our domain. So what we need is the part underneath our radical has to be greater than or equal to 0. Everybody okay with that? Okay. So if I rearrange this, I can add 2 to both sides. And my domain, I'll label this as domain, should be the x's that are greater than or equal to 2. So I'm going to now write that in interval notation. What is the lower bound of the numbers greater than or equal to 2? What number is less than or equal to all the numbers that are greater than or equal to 2? 2, right? Everybody agree with that? What's the upper bound for the numbers that are greater than 2 or equal to? What? Not 2, not 3.
What's the question?
Then what is the upper bound for the numbers that are greater than or equal to 2? Huh?
Upper bound?
Yeah, it's got to be bigger than everything that's greater than or equal to 2.
3 or higher?
It's infinity, right? Because there is no number that's bigger than all of those. We call that concept infinity, right? Everybody's okay with my upper bound and lower bound, how we came up with that?
Yeah.
All right. Now, the set of numbers that are greater than or equal to 2 is 2 greater than or equal to 2?
Yes.
Yes. So it should be included it should get the bracket. Infinity always gets a parenthesis. It's not an actual number. It's like a conceptual thing. Infinities will always get parentheses. So there's our domain. Everybody's okay with that? Okay. Let's talk about our range now. So a range is going to be all the possible... Yes, sir.
I just want to say you explained this way better than what we were explaining last year. It's like actually...
Or sometimes just hearing it the second time helps too. But we're trying. Try very hard to do it like slowly and carefully. Yeah. It's also like, I don't know, this is I think year like 15 or 16 of teaching. So imagine like doing the same class for like 15 or 16 years in a row. Like how good would you be at explaining things?
Do you just do this like the same thing every week?
I mean, this stuff gets taught, I think, in every class. Every math class at some level, you do this kind of stuff. So you just get, this is like foundational kind of. Conceivably, you could do an Algebra 1, Algebra 2, trig and pre-calc, AP calculus, like a bunch of, this just happens all the time. So like this part gets done. I've probably done it every year that I've taught. Okay, the range now. The range is our possible outputs, our y coordinates, right? First thing I want to decide is whether my function here, y equals the square root of x minus 2, is that always increasing or always decreasing or sometimes doing some of both? So let's think about the square roots of numbers. So square root of 0 is 0. The square root of 1 is, the square root of 4 is, the square root of 9 is. What are you noticing as the things under the square root are getting bigger? The square roots are also getting bigger. So it's increasing, right? So that tells me then the smallest input or the smallest thing in my domain is going to give me the smallest thing in my range. So to find my lower bound over here, all I'm going to do is plug in that 2 into my function, and that's going to give me my lower bound. Everybody's okay with that? And since my function is increasing and the upper bound is infinity, what's the upper bound for the output have to also be? Still has to be infinity, right? If it's just getting bigger and bigger and bigger, and I can get as big as I want as an input, well, I can better get as big as I want as an output. Everybody feel okay there? Yes? Of course. Reagan, right? I'm just practicing names.
Yeah.
It's not, I don't have anything to say other than yes. Go ahead. All right. The last thing we need to do is decide whether we need parentheses or brackets. Infinity, always parenthesis. That's easy. 0. Let's think about this for a moment. I got this 0 by plugging 2 into my function, correct? 2 came from this 2, which had a bracket on it. So I get a bracket on the 0. Is everybody okay with that? So I'm just tracing back. How did I get that 0? A number with a bracket on it. That'll get a bracket too. Does this feel okay? Okay, so that's kind of how we do interval notations. That's how we do some domains and ranges. Let's do, I'm going to give you some, I'm just going to give us some inequalities, some sneaky inequalities, and we're going to translate those into interval notations because it's easier than me cooking up a function that does it because it gets too complicated. So let's do this. And I want to just translate this to an interval notation. So the lower bound here on this inequality is -5. The upper bound is 10. The -5, should I get a bracket or a parenthesis? Is -5 less than -5? No, right? So it should get a parenthesis. How about, is 10 less than or equal to 10? Yes. So the 10 should get a bracket. Does everybody feel good there? So in short, strict inequality, parenthesis, or equal to inequality, bracket. Means the same thing. So remember from algebra, these are, when we write the inequality this way, this is the and inequality, where you're greater than -5 and less than 10. The other type of compound inequality that we see is the or inequality. Now, this is a little bit more complicated, right? Not quite as clear what to do right away. If you're stuck, like you might be looking at this, a good place to start would be to try drawing the inequality on a number line. So remember, like the number line? Just like write -2 on here, and we'll write +5. So do I put an open circle or a closed circle at -2? Open, because it's a strict inequality. Very good. And then a is less than -2. Should I be pointing to the left or to the right? Left, because the numbers that are less than -2 live left of -2 on the number line. Okay. And then let's look at the other part. So a is greater than or equal to 5. At 5, should I do an open circle or closed? Good. And then should the arrow be going left or right? Right. Everybody's okay here? So what I'm going to do is I'm going to treat these as two separate intervals. I'm just going to write this interval, and then I'm going to write that interval. And in between them, I'm going to use the symbol U. So or is just going to turn into this U when we translate this inequality from an inequality into an interval notation. Everybody's okay there? All right. So if I look at that first part on the number line, the smallest number in that piece of the number line that we have is the lower bound, which is not -2. That's the biggest because it's the furthest to the right. What's the number furthest to the left? -infinity, right? Because it keeps going there forever. So -infinity and then -2. Now the infinities always get a parenthesis. Should the -2 get a bracket or a parenthesis? Well, the circle is open. Meaning not included, right? The inequality was a strict less than, should be a parenthesis. Is this feeling okay? Okay. Let's look at the next piece. What's the smallest value on that section? 5. That's the lower bound. And the biggest value or upper bound is +infinity. Excellent. Okay. The infinities always get a parenthesis. And then the 5 should get a parenthesis or bracket. Bracket. The circle is filled in, or it's a greater than or equal to inequality, so we know that gets a bracket. How are we feeling? Pretty good? Okay. Let's do another domain and range problem. Well, Of course, yeah, of course. Where are we at time-wise? I'm still doing pretty good, aren't I? 12:40. Okay, good. That's fine. All right, because this is the last thing in here, right? Yeah. Okay. Good, and that's easy. Okay. What I want to do now is talk about a little piece of vocab when it comes to this. Yeah. So we have something that is like called an implied domain versus something called a relevant domain. So our implied domain is going to just be the values that are like algebraically possible. They're going to be the values of x that I can plug into the equation, whatever the equation is, regardless of context, that give me a defined output. The relevant domain is going to also take into account context. So if my function is, taking height of the individual and outputting weight, the relevant domain has to be positive values because nobody can have a negative height. Even though the function, the equation that might be following might be fine to plug negative numbers into, but it doesn't make any sense in the context of the problem to plug a negative number into this. Does that feel okay? So this is just like, like context matters, right? The words, the scenario that the function is describing matter. Okay. So for example, if we do this guy, there's no context here, right? It's just g of x is equal to stuff. I don't know what g is saying. I don't know what x represents. There's no context to this problem. It's just it's just symbols, right? So here I'm just worried about an implied domain. So are there any values of x that are going to give me any trouble if I plug them into this equation? Be careful. There's one value of x that's going to be a problem. 0 is fine. Most negatives are fine. So the operations going on in this problem, let's back up a little bit, right? The operations going in this problem are multiplication, division, and addition. Can I always multiply two numbers together and get an answer? Yeah. Yes. Can I always add two numbers together and get an answer? Can I always divide two numbers and get an answer? No. What one number is a problem if I try to divide by it? One number is a problem if I try to divide by it. 0. Excellent. Anything divided by 0 is undefined. So the place where I'm going to have a problem in my implied domain is going to be when this is equal to 0, right? Specifically, my domain is going to be everything except when x plus 2 is equal to 0. Right? Now, how the heck do I represent that with an interval notation? That's not very clear. Well, what do I do when I'm stuck? I try to draw it on the number line and see if that helps me. Okay? So if I draw a number line, here's -2. X cannot equal -2. So -2 definitely has an open circle, right? But anything other than that would be fine. So I can have arrows going in both directions from that. Everybody okay? Okay. So just like we did for the OR inequality, I'm going to do an interval for that piece and then an interval for that piece. And what goes in the middle? That U symbol. So if I look at the green part, the lower bound or smallest value there is -infinity. And the upper bound or biggest number is -2, right? Because it doesn't have to be able to equal it. It just has to be like, that's the boundary. Everything else is, right? Because like -2.5 is in there, but that's bigger than -3, right? So -3 couldn't be a lower bound. Parenthesis gets, or infinities always get parenthesis. How about the -2? Parenthesis, because we used an open circle. Now let's do the yellow. The lower bound is, and the upper bound is. Excellent. Always a parenthesis on the infinity. -2 gets a parenthesis. There's our domain. You feel good? Feel good? No? Too fast? It's okay. We'll do more. Now, what if I have my function is v of s equals s cubed, where v of s is the volume of a cube with side length s. Do I have context in this problem? Yes, right? S represents an actual thing. V of s represents an actual thing. These aren't just arbitrary numbers. These are quantities that have some kind of meaning in the real world. So here we're going to be doing a relevant domain. Okay? What does S represent? The side length of a cube, right? So what values can S take in the real world? Positive values. Everybody agree with that? Can't have a negative side length for a cube. I'm not sure I would call a cube with 0 side length. That'd be a single point. I don't think that should count either. If you argued that it did, it would be fine. Like, close enough. So, all we have to do is convert this into an interval notation then. What's the lower bound? Zero, right? The upper bound is positive infinity. Infinities always get a parenthesis. The 0 should get a parenthesis. The strict inequality always is a parenthesis. And we're done. That's our domain. What if I wanted a range out of this? What does the range variable? V of s. Excellent. Yes. That's our range. And what does this represent? Volume of a cube. What kind of values are acceptable for a volume? Positive values. Now, would I expect volume? You know what? It doesn't even matter. They all have to be positive, right? Can I input any positive number into there? Yes. So any positive number should be able to come out. So the range should be the exact same thing. And I'm done. So these relevant domain problems should be pretty easy, but you have to think about it. You have to use like what you know about the real world, the quantities involved. Okay. this is supposed to end at 12:40. I thought 40 on my list. Yeah, 12:40. Okay. Lunch starts 12:45. Oh, 40. Yeah. Okay, good. Yes, agreed. All right. Brain break. I want to talk about continuity. This is all definitional continuity. So all we're going to be doing is like making some vocab and looking at some pictures and deciding which picture meets the criteria, whatever. Okay. So when we say a function is continuous, it just means that we should be able to draw that graph without picking up our pencil. So remember when we drew y equals x squared plus 2 earlier? That's continuous because I can draw the parabola without having to pick up my pencil. Everybody's okay with that? If you can't do that, we say that that kind of function would have some kind of discontinuity in it, where there's a break in the graph somehow. There's 3 types of discontinuities. There is the infinite discontinuity. We also will call these vertical asymptotes. If you remember that term from last year, did you get that far? Okay. Rational functions usually have a vertical asymptote. Logarithmic functions have vertical asymptotes. Let's draw a little picture of what we mean. This dashed line that I drew here is my infinite discontinuity. That's what it would look like. Yeah, I would think you would have, but every year it's different what we get to. There's a removable discontinuity. And we did this earlier. Or I showed you an example of it earlier. Where I have this little gap in my graph where it's missing a point somewhere. That's a removable discontinuity. We just looked at that earlier when we were talking about functions and how I could make it tricky or whatever. And then we have something called a jump discontinuity. And that's where it's kind of like we have a removable, but instead of the other piece matching up, it's just offset. So it go like this, pick up my pencil and then start up here. Notice here that one of them is open and one of them is closed. Could they both be open? Yes. Could they both be closed? No. Why not? It would fail a vertical line test. Yes, you'd have 2x or 1x with 2 different y's. Would not be a function if they're both closed. That can't happen. But both open is fine, right? It just means that the function is undefined at that value of x, but so what? That can happen. That's it. Your problem set. Again, this isn't due till next Sunday. We're just seeing it for the first time today. So we'll start with the numbers 1 through 12. 1 through 12.
In the problem section.
Yep. You can, okay, so all your homework is going to be turned in through OneNote. You can do it on a separate sheet take a picture and then load the picture into OneNote. We'll show you how to do that. You can write it directly in the homework section of your notebook. Try to label the section as like, like numbers 1 through 12 or something, so that it's like, I know what it is. Either is fine. Do whatever is easiest for you. If you're not sure what to do, we'll talk about it on Tuesday or something. Okay. Jake.
So is there only homework due next Monday, 1 through 12, or are you going to assign more next week?
So next week on Tuesday, I assign something else. That would go in there. Thursdays would not, because we wouldn't have a day of class to ask questions before the homework would be due. So Thursday's assignment would go into the week following's problem set. That kind of the pattern. So I always want at least one day in class before anything is due. Fair enough? And now I'm done with you guys. In the future,